All right. Thanks everyone for showing up for the afternoon session on 3D and immersive visualization. Our first speaker is Charlie Wang from University of Notre Dame on IVRGS inverse volume rendering for explorable visualization via editable 3D Gaussian splatting. Go ahead.
Okay, thank you for introduction. So we'll be talking about IVRGS. So if you look at the computer vision, right, in the space of normal view synthesis, right, so one popular technique is called the neural radiance field or NeRF. So essentially, what it does is to using the MLP neural network to get a sample from the 5-dimensional XYZ, theta, and phi, and try to reconstruct the color and the density. Essentially, use that information, you do volume rendering. So the good thing compared with traditional volume rendering is that you don't rely on original data, but rather, right, a couple of sample view image, you can do this normal view synthesis. NeRF is good, but it's very slow, okay, because use fully implicit neural network. Another technique is called Gaussian splatting. Try to solve that problem. It can be rendered very fast interactively during the inference. So the idea is, Gaussian splatting doesn't use neural network at all, right? So rather it's using millions of Gaussian points, and each point, as you see here, right, can be represented by the P, that's the point here, and to keep track of the mean value, and also using this covariant matrix that can be aligned and stretched in any direction to do the feedings. So it's fast compared with NeRF because if you do ray casting, you get a bunch of splat. So rather than you have to sample 1 voxel by 1 voxels. So this is come from original 3D Gaussian splat papers. So it's pretty flexible, as you can see, right? So if you have the outline, that's this small geometry. So the splat can be chrome and then fit into the shape, or if the splat is too big, right, it can split and also try to fit the shape pretty well. So in visualization, right, there's an existing word doing something like visualization generation or novel view synthesis. There's some limitation. So the first thing is these are really constrained by the transfer function. It's all mostly depend on the given transfer functions. The second thing, right, lighting and transfer function are baked into the model representation, which means you can't change it after you train the models. So our goal is try to change that. So make the scene editable. So which means once you train it, you can actually tweak those parameters as you are with traditional rendering, where you have the data at the back end. And also, there's you either get the model, right, it's very fast, but the model size is big, or vice versa. So you can get both. So we want to propose this IVRGS. The main idea is to create this, we wanted to come up with some basic model. With basic model, eventually they train separately, right, for different part of the transfer function. Eventually, once you train the basic model, you can compose them effortlessly. So you are able to create a scene. So we also introduced this editable Gaussian primitive. Basically, once you train the model, you can tweak those lighting parameters and generate new visualizations. Also, right, so like the DNN Wolfish, it can do inverse Bourne exploration. So given a target rendering, right, so we don't know the transfer function, and the model can learn to generate similar visual effect. So we also use vector quantization to compress the model without lose much of quantity, and we can compress the model, say by 7 times or 10 times. That can reduce the footprints. So the basic model for this IVRGS is that, so we do a very simple model. If you look at the transfer function space for different value ranges, we just model one basic scene as we see here, right? So we have 3 examples here with a spike that try to model that's particular value ranges. And each of these are trained independently, and this come from, again, with multiple image as the input. So it has nothing to do with the data. But when you generate images, right, after you generate image, train the model, so the model can be composed, can be added. So for each of this model, what we do is we train those Gaussian parameters. We consider those geometric attributes, including the spatial mean, the covariant matrices, which can be broken down into rotation and scaling vectors. Also, we consider the opacity, adding this normal vector for the lighting. So these are learnable parameters associated with each of the Gaussian splat. In terms of shading, right? So every basic model have the kind of like palette color. And for each of the Gaussian splat, right, we learn, we call it offset color. Basically, you can deviate from the reference color. And also we using this bring form lighting models. So those are standard ambient diffuse specular coefficient, shyness coefficient, that can be learned as well. So once you learn the model, right? So at runtime, you can actually just turn on, turn off each of the basic model. You can compose it, right? If you turn on everything, the volume will be fully opaque. And then with that, right? So you can do real-time, we call the scene editing. As if you are doing traditional rendering, you can adjust those lighting parameters. And you can also do what we call the inverse rendering, which given a reference image, we can mimic, right? We can use the basic model to mimic the final rendering effect. So which is good because oftentimes if you see some good rendering, right? So you like it, but you don't know the transfer function. So this one try to basically to mimic the same renderings. Okay, so these are the interface on the left. It's just like a typical volume renderer. Again, this is based on Gaussian splatting. There's no original data. There's no doesn't depend on original data, just based on the multi-view image training images. On the right, there are a couple of parameter panels, right? So you can do the rendering option. You can do color editings. In the middle, right, it's like a transfer function. So each of these blue bar is basically control the basic model. So you can turn on, turn off, and changing the color, and so on and so forth. At the bottom, you can change those lighting parameters. Will there be a video?
This paper presents IVRGS, an innovative novel view synthesis framework that supports user exploration of the volume visualization, or VULVIS, scene. Scenes represented by prior novel view synthesis methods are limited by the preset transfer function that generates the multi-view training images. IVRGS overcomes this limitation by designing Gaussian primitives to represent editable scenes over different voxel value ranges and compose them together. After composing, the entire VULVIS scene is visible in the composed IVRGS model, and users can flexibly edit the color, opacity, light angle, and magnitude of the IVRGS representation to explore the VULVIS scene. Meanwhile, IVRGS incorporates the Blin-Fong reflection model within its representation. Users can also check different Blin-Fong terms within our interface.
Okay, so some of the additional technical details. So in terms of the capturing the sampling view, we are using ISO icon sphere. We start with 12 view. If you need more view, we can subdivide further, right? Generating 42, 90, 92, and so on and so forth. So these are the loss incorporated into the training process, right? There's normal consistent loss to capture the normal, regularization loss, sparsity loss, and bilateral smooth filters. Okay, so in terms of the scene composition and editings, so we store the palette color as global parameter for each basic scenes, right? So, and we achieve these composabilities by spatially composing those editable Gaussians. User can adjust those color opacity and lightings. In terms of inverse volume exploration, right? What do? We freeze those Gaussian parameters, okay, from the trained models, and we basically learn some kind of scaling and also translation for each of the model, and each model will be trained to fit together, right? To fit into the target visual effect. Okay, so these are some of the data set we're exploring. The data can be really big, right? Can be up to 32 gigs. So if you render this using traditional data volume rendering, you don't get even 1 frame per second. And in terms of the baseline, we compare to Phenoxos, okay, and CCNeRF. And also there's a basic 3D GS model. That's still the basic IVR-GS, but there's no editable capabilities. You look at the comparisons, so we get actually the best in terms of the qualities, okay? And these are the rendering time. It's really, you can achieve very high rendering rate during the runtime over 100 frames per second. And the model size is much smaller, okay? So it's like typically 10 megabytes. So here we show the comparison. So obviously, right, so IVR-GS is better than Phenoxo and CCNeRF. It's similar to base 3D-GS, but base 3D-GS only have this composability, right? They can reconstruct the scene, but there's no way to edit the scenes. Okay. And here just show you the lighting part can be decomposed with our models. For the scene editing, these are the experiments we do. Okay, so you see that result. This is one result. You can actually change in the light directions, right? So you move the light from bottom to top, right? So compare with the ground truth, and we can faithfully reconstruct the scene with the lighting changes. And another example is this inverse volume rendering. These are you just provide one reference images, right, with the camera viewpoint, and we can learn through that. And these are the ground truth. These are the IVR-GS learned result. You can see they are very close. So some of the limitation, right? So the size of model is depend on the number of basic the models. So sometimes we need to go to more than say 10 models, but you have to use compression to reduce the model size. And we just use uniform sampling for the camera viewpoint, but you can do that non-uniformly. Maybe you can use field point, but to capture the scene much better. Also, it depends on the lighting model as well. Okay, so these are the last slides. So we present this novel framework for supporting exploration without access to the original data using Gaussian splattings. So the idea is composable and editable for the Gaussian splatting. We produce high quality results, real-time renderings at the inference times. In the future, we want to incorporate that to with style transfer. So and also tackle dynamic or time varying volumetric things. That's all. Thank you.
All right, we have time for one short question. The mic.
Hey, so I had a question for training. First off, how do you decide how many ranges to split your volumetric data set into? Like how many models you need to compose? And then also, is the training for each of these models that you're composing, do those happen off of one set of ground truth images that, like the ground truth images are rendered for all values of the scalar range? Or is it like some images of like split into different ranges?
So the first thing is, so in our paper, we tried, like 2 or 3 basic model. That's the mean. On the max side, you can go for tens of models. So obviously, if you want to do a more refined control, right? So for some data set, you want to train more model, but it takes time to train those models. Each model is trained independently. For each model, you capture multiple view, right, from that particular visible transfer function. So, but once you train that, you can simply just concatenate those models together to compose the final model.
Let's thank the speaker. Let's move on to the next one. All right, so our second speaker is Junxiang Yao from Fudan University, and he's going to talk about DTBIA, an immersive visual analytics system for brain-inspired research.
Thank you, Professor Wang, for the introduction. Good afternoon. I am Junxiang Yao from Fudan University. Today, I would like to introduce our work, DTBIA, an immersive analytics system for brain-inspired research. Oh, big thanks to my awesome co-authors and my supervisor, Simin Chen. And this work won't be possible without their help. All right, and let's get started. So first thing is, what is the DTB? In brain-inspired research, DTB stands for the digital twin brain. It's an advanced AI framework that models both the function and structure of the brain. In this work, we simulate our human brain. Think about that. Our human brain weighs about 1.5 kilograms, but contains roughly 86 billion neurons, and each neuron connects to tens of thousands of others. Yeah, we are talking the world's most complicated network sitting right between our ears, but we still know so little about how it really works. So as Richard Feynman said, what I cannot create, I do not understand, so we want to create them. But building such a complex network takes teams of experts from different fields. First, neuroscientists collect the brain scans to build our training data sets. Then our math experts build the math framework that forms the model's backbone. Finally, our computer scientists run the simulations on massive computing clusters. And this is exactly what our ISTP team is working on right now. Next, let's take a look at what the DTB can do. With DTB, we can start to explore the emotions such as what makes us happy or sad, as well as the perception and connection like how we see, we test, and we learn and remember. DTB also serves as a bridge between the biology and AI and has potential to power the next generation AI, or maybe we call it the AGI. It can power anything in various applications like self-driving cars, and smart medical systems or adaptive robots, etc. By simulating real brain activity, we hope to both understand ourselves more and build a machine that think more like us. There's a simple overview of the DTB pipeline. Basically, it's a bottom-up simulation process, building from the individual voxels to the whole brain model. The output data can be divided into two categories. The first is the functional data. These are the dynamic time series, showing the rise and falls over time and in each voxel and regions. The second is the structural data. These are the static connectivity maps, showing which voxel and regions are linked by the neural pathways. In this work, our motivation is for the past 2 years, we have collaborated with the ISTP team using the visual analytics to help domain experts to explore the DTB data. Our team's previous work is on the left is called the DTBVis. It's based on the traditional desktop. But the expert point out two issues. First is the AI expert without an biology background struggle to perceive the 3D structure of neuron pathways. And second, a limited flat 2D screen just cannot effectively display tens of thousands of nodes and connections. So we consider moving our DTB analysis into the immersive environments VR like Sonia. And we can give users the true spatial context and let them interact physically with the data and make it much easier to find patterns and share insights. Ensure we let experts step inside their data. And here's a quick demo of our system. On the near side, you can see the real scale brain displaying the dynamic functional data. And on the far side, present the large scale brain visualizing the static structural data. Okay, next we have a quick data description. In the brain structure, we use the AAL atlas to split the brain into 92 regions, excluding the cerebellum, which is in the back, and which gives us a total 22,000 voxels in total. And for the functional data, we have both biological brain and DTB data samples the resting state board every 800 milliseconds over 166 time points. For structural data, we generated a fully connected DI matrix across all voxels. Then we collect the experts' needs. Our collaborated ISTB team includes 8 math and CS experts and 2 neuroscientists. For the math and CS group, because they are focusing on the simulation validation, so they needed tools to spot value patterns and iteratively refine the model. On the other hand, the neuroscientists are identifying voxels and brain regions that show the activation burst. Across both teams, there are a shared need for a top-down workflow that is start with the overview and apply filters to drill down to the detailed on demand. So we identified 3 main challenges. First, bridging the gap between the AI experts and neuroscientists was difficult because the AI expert without a biology background often struggle with the spatial context that is needed to discuss the brain anatomy. Second, the large number of connections leads to the overwhelming of visual complexity, so meaningful patterns may get lost in the sea of lines. Third, currently navigating between whole brain overviews and detailed view has no intuitive way to transition between scales. To address this challenge, we first designed 2 navigation modes for the immersive environments. First, in the exocentric mode, expert can walk around a real-scale brain to observe the dynamic both signals. And second, in the egocentric mode, we can fly into the large-scale brain to explore the static DTI connections. With these 2 modes, the experts can seamlessly switch and land at exactly the right position and orientation to explore either dynamic or static data. And the second challenge is from the dense connection links. So the system first applied the threshold to binarize the network. Those filters links are then processed into a 3D first-directed edge bundling algorithm, which aggregate nearby fibers into smooth bundles. And those the button shows the top 10% of the connection, and the links are color-coded by to indicate the 3 principal directions. Then we introduce our top-down workflow. It's organized into 3 hierarchical exploration level. It's region, voxel, and select sections. So at each phase, users can seamlessly switch between the real scale and large scale brain models. Next, I will walk you through how the exploration process at each of these levels. In the first region level, the expert first compare both signals with the side-by-side placement. Left is the biological brain and DTB is on the right. Expert can then select the regions they are interested in. To see the connection up close, expert can then navigate to the large-scale brain, and the panel in front will show the connection ranking by the weight. Expert can repeat this process and collect all the regions for the next step analysis. And here's a short video to demonstrate how it works. And the first, the expert can find the peak activity time points, and at this specific time point, they can find the regions they want. And then they can iteratively find the relative regions based on their original region. In the voxel level, because we have so much time, so we can just see the video. So in this voxel level, expert can first select the brain region, and then they show the voxel within that region. And they can play the encoding animation of both. At the same time, the static 3D line charts showing the average both signals will be displayed in the large-scale brain. And that is a FDEB connection from those voxels and color-coded by the connection weights. And also a threshold slider lets experts to focus on the most significant pathways. Last, in the select section phase, expert can use three slicing planes combinations, that is sagittal, coronal, and horizontal to cut through the brain. And in this situation, he chooses the coronal, and the voxel on their slides will be displayed. The bold and DTI will be displayed also. To validate our system, we conduct two case studies. The first involved the AI experts without the biological background to assess the core functionality. And the second case involved neuroscientists to explore deeper domain insights. And we have 12 participants in each study, and 2 experts were the head multi-devices, while 10 additional experts watched the live stream of their view. During the study, users in HMD are encouraged to think aloud. They can describe what they saw, what they experienced in the real time, while others could ask questions or other suggestions via the share screen. Our results showed that experts were able to carry out DTB analysis effectively and they rated the system with high learnability, usability, and overall satisfaction. In the immersive environments, they reported the enhance of spatial awareness can bring deeper level of engagement and understanding. In the future work, we plan to expand our data set with additional modalities such as EEG or MEG and push spatial resolution down to the cortical microcolumns to reveal patterns below the voxel level. We also plan to include text-based data, for example, auditory or visual stimuli, rather than relying simply on the resting state. On the interaction side, we will add multi-user VR support. Also, we find some users may experience VR sickness during the navigation, so we will refine our documentation option to make the experience with more comfort. Finally, the takeaway in this work, we partnered with 12 experts to bridge the brain-inspired computing and neuroscience, which advanced the DTB research. Secondly, we developed an immersive analytics system that streamlined the cross-domain communication. Lastly, 2 case studies and the expert feedback validate the system's real-world value. And that's all of my talk. Thank you for your attention. I'm happy to take questions.
Any questions? Go ahead, please use the speaker.
Yeah, so great talks, and it's really impressive system, by the way. It's so many data and everything. So at some point we should discuss about this edge banding technique because you're using force-directed one, and that's not really the actual one, and the far more efficient one. But my main question regards the way that VR is so important for this type of system. So because I don't know, if you have multiple screens, you could do something similar in terms of exploration and using the VR. So I would like to get more feedback from that, how the users really react to that, because in the experimentation, you told us that they looked at the screen while someone operated with the VR headset, or there's this notion of motion sickness, and also how everything is complex, in fact, to retrieve any information. So what is the key features for VR here?
So in the very beginning, we use the web-based systems to visualize all this stuff, and we find that when the data is large, it's getting more and more, the performance will get low. So we are now using the Unity based, and we find that in the VR environments, we usually just use the filter to low down to decrease the amount of the edges, and we can use some interactions like we just look some maybe color coded in the red edges, and we can just collect them the pathways or something. We can just use, I think we can in the VR environment. I think the important way to interact with is the embodiment style.
So we're going to move on to the next speaker. The next presentation is going to be remote. And it's going to be given by Jingjing Jiang from Fudan University. And then the title is Social Media Island, Interactive User Profiling and Information Diffusion Exploration with 3D Visual Metaphors.
Thank you, host, for the introduction. Can you hear me? And can you see the screen? I see you can see the screen. Can you hear me?
Yes, we can hear you. Please go ahead.
Okay, so good afternoon, everyone. I'm Jingjing from Fudan University. And today I'm going to share our work of Social Media Island, which is about a interactive user profiling and information diffusion exploration with 3D visual metaphors. And we're going to start from the motivation. With the increase of social media platforms, data generated from them becomes more and more complex, and many works focused on constructing visual metaphors to solve some of the intriguing tasks, such as building user profile or forwarding structure or finding semantic evolution. It is natural to try to utilize 3D when dealing with the multidimensional data, but people are discouraged by the limitation of 3D visualization. And we think because of these changes, especially the XR technologies and the growing demand for diverse data comprehension, it might be a good time for us to reconsider the power of 3D visualization, and that's why we propose our work. Here's some works that we found related with visual metaphors. And we can see there are some certain metaphors that are naturally inspired, such as mountain, a river and tree, flowers. And also there are some society-inspired parts, such as cities and maps and all kinds of glyphs. And these papers give us a general impression on how the visual metaphors help users to grasp key characteristics hidden in the data in a more immersive and vivid way. And we also did some research on the social media analytics, and we highlight 3 main challenges that we're going to cover in this paper. Start with the contradiction between visualization of very semantic information and the forwarding structure. And the second one is the lack of highly conclusive user profiling visualization to help compare multiple users in a conclusive way. And the last one is the inability to support the scaling scope and also control the mining depths. And we use a user-centric data set brought from Weibo, which is a Chinese social media platform. And all the tweets that we collected are from the same person, which is called a root user in this paper. And we also define some of the other terms like impact and layer and participants. And in order to solve these challenges, we set the following 3 design requirements prospectively. And here's the key visual metaphors that we design. And before that, I'm gonna tell more about the general design of 3D metaphors. And we all know that 3D visualization has certain inherent limitations, such as perspective deformation and object occlusion. And we try to summarize 3 application scenario where the performance of 3D visualization is better than 2D ones. And then scenario 1 and 2 is when you need to visualize complex data with spatial layout or hierarchy structure or multi-dimension. And then scenario 3 is when we need to focus on design immersive and intuitive interactions for users to explore. And we summarize the design space of building a 3D metaphor, and we divided the attributes into 3, including position, appearance, and interactions. And besides, we conclude 4 principles and 3 characteristics to build a better 3D metaphor. And the first one that we design is mountain in this paper. And the mountain is to generate a conclusive visualization for one user. And basically the process has 2 parts. First, we need to arrange those tweets into data points. And this is a tweet, and we align all the tweets with similar topic in the same radial direction sorted by time. And after that, we do some data processing and divided all the data points into data blocks. And for each block, we use a Brazil algorithm to generate a Brazil service and combine all those services together to build a mountain surface. And during this process, we kind of have multiple tries, and we tried using convex or using different kinds of curves. And finally, we find the Brazil curve, which has the best performance here. And we define certain interactions which are all cuts but in different directions, like cutting height to see those tweets with similar impact, or cutting circular when we need to dig into tweets with same time period, or radio cutting to get those tweets in the same topic. And the next metaphor is tree. The tree is designed to quickly grasp the pattern and the distribution of the hierarchical structure in a vivid way. And the idea is quite simple. We just switch the node in a forwarding structure into a branch in a tree. And you can see the branches grow according to the number of reposts and show different patterns and features, which is pretty fascinating. And this is a tree shown in a 3D way. And when you get a lot of trees generated in one space, it's kind of like a forest. So you may notice it's beautiful, vivid, but it consumes a certain amount of information that makes people hard to compare in detail. And that's why we introduce a ripple metaphor in this paper to make up for the deficiency of tree metaphor. The construction logic is pretty same as the one with the tree, and we label the possible semantic evolution point, and users can further compare in a more accurate way. And put these metaphor together, we get our social media island. And you can see the workflow here. The whole data process that we did before are listed on the left part of the chart. And the right part is about what information users gonna get from different gestures. And you can see we have 3 major interfaces in the system, and users can switch interfaces when exploring in a social media island. And after entering the system, users can see the initial interface where they can expand as many single trees as they want. And then users can get into the selection interface and select the cutting method that they want and cut the mountain. Cutting will keep all the tweets related remain in the system. And this interface is called cutting surface interface. And users can further expand the ripple structure and for details to compare there. And the next part is about evolution. And we did our user study on the effectiveness of visual metaphors. And by case study, we found some certain patterns in, for example, the tree metaphor. And you can see this is a comparison of 2 metaphors that we designed to show the same structure. And it is clear that 2-dimensional multiples enable users to do detailed comparison and to observe the difference and trends more clearly. And 3 multiples facilitate users to gain perceptual cognition in spatial and topological way. And we found 2 typical patterns as well. Type 1 is more like a circular wheel. Usually it means the tweet fits the general opinion of the user and is more likely to be a communication within the community. And on contrary, type 2, which features like a slender bouquet, is more likely to be an in-depth debate happened in a crossover diffusion situation. And based on the data set that we use, we did some user studies, other case studies as well, and we get to know the interest of our root user includes politics, entertainment, educations, etc. And by cutting the mountain in a radial way, or simply clicking all the tweets in the same radial direction, we can observe the consistent interest
So you
shared
have
by
2 minutes left.
Yeah, thank you. By our root user, for example, over Chinese traditional calligraphy work, and observe a discussion over a similar event happened and be discussed over a time period. And we have reflected the implication that we gain from this study and also the limitation of our work. And we also implement this system into an immersive virtual reality environment, and we can find combined with VR technologies, 3D visualization provides a more intuitive and engaging experience, allowing users to freely explore patterns from different views and just like wandering in a scene generated from the abstract data that may be impossible to grasp using just 2D representations. And that's all. Thank you for listening. If you want to discuss anything, feel free to contact me or my group.
All right, thank you very much. Any questions from the audience? So I have one question. Towards the end, you turned all your 3 visual metaphors the mountain ones, the tree one, into this sort of immersive environment. Do you have something to say about the effectiveness among your 3 different type of metaphor? Is your user study that discuss what's sort of effects?
Actually, we just did our user studies on the effectiveness of visual metaphors alone, not on the system. But we invite a certain amount of, but limited amount of students to experience our system in the visual reality. That's our limitations that we mentioned in our paper.
Yeah, it would be great to see a comprehensive user study in the immersive environment.
Yes, thank you for your advice.
All right, thank you so much. So we'll move on to the next speaker. So our next speaker is Tika Ling. I know he was here earlier. Okay. Oh, yes. Okay, so Tika Ling is from Harvard University, and he's going to talk about Sports Buddy, designing and evaluating an AI-powered sports video storytelling tools through real-world deployment. Please go ahead.
Can you hear me? Hi, good. Hello, everyone. I'm Rushin, and I'm here to introduce Sports Buddy, our AI-powered sports video storytelling tool through real-world deployment. And this is our UI to give a very initial impression. And I'm going to introduce Sports Buddy through 5 key sections: why Sports Buddy, our design goals, our visualization design and system design, and finally some case studies. So, why Sports Buddy? Videos deliver values in the sports world. It helps sports professionals to drive performance. It captures and analyzes key moments to refine skills and strategy. It delivers fast visual data for decision-making and improvement. And it creates shareable, captivating content that resonates. And there's a huge demand for sports highlights. Coaches, athletes, and fans want to share key moments at just the right time. Short-form content thrived on the video platforms. And as viewers, visual aids and narratives make the insights engaging and more appealing. However, creating highlights is still a challenging task. This is because existing editing tools often have like steep learning curves, such as the Final Cut Pro or Adobe Premiere Pro. And most tools are not built with the athlete or coaches in mind. And managing disjointed process slow down the insight sharing and decision making. So we set to solve these issues by designing Sports Buddy for sports professionals and fans. We have 4 design goals. First, intuitive sports features and interactions. Traditional video editing workflows is quite overwhelming. For example, it takes 5 steps to adding an arrow. First, navigate to the menu, and second, drag the timeline. Third, adjust some settings. Fourth, apply some animations, and finally, an arrow. However, this process is far less intuitive than how sports experts simply draw some signs or arrows on a tactical board. That's why an accessible tool should be simple, interactive, and with context-embedded features that's clearly aligned with user intent. Goal 2, object-level visualization. Imagine we want to highlight a player. How do we do that? Traditional graphic level video editing tools forces creators to manually track player movement using a separate spotlight layer frame by frame. If you are like familiar with the video editing tool don't want to do that. However, insights are best communicated with a human touch. Players are the main characters. That's why we want to attach visualizations directly to players, enabling a player-specific or object-specific highlight. And goal 3, seamless integration of visuals and narratives. Sports insights are typically shared through visual highlights, tactical drawings, and narratives alongside the original game footage. So our tools should help users integrate all this into the game footage for dynamic data-driven game analysis. And the last goal,
to present as first of all, existing this increasing as receive this is such as positions and the second is disconnect how tools for instance this is system discuss others
A spatial temporal data story often involves multiple scenes and viewpoints at different scales, along with various types of data and visual elements embedded within each scene. To manage these components efficiently during the authoring process, we need a framework that can systematically organize them. Given the inherent spatial-temporal relationships among these fragments, a hierarchical framework is particularly well suited for this purpose. Our proposed three-layer narrative structure consists of storyline, story piece, and the viewpoint, which together help story authors maintain control over both the macro-level direction and the micro-level details of their narrative. Using this narrative framework, story authors can first conceptualize the main themes and the narrative flow as storyline, and then select key spatial temporal scenes for the narrative as story pieces, and finally design each story piece in detail by defining the key perspective for the audience as viewpoints. In our framework, we mainly consider two types of transitions, the transitions between story pieces and the transitions between viewpoints. Through these two types of interpolation-based transitions, the generated story consists of animations involving the smooth change between spatial temporal scenes and the continuous motion of the camera. Okay, and so to address the challenge of the mismatch between the authoring environment and the viewing environment, we proposed the ST Squad VR, an immersive spatial temporal story authoring system guided by the hierarchical narrative structure. It consists of two interactive interfaces, the inter-story piece interface and the intra-story piece interface. The inter-story interface supports the creation, deletion, and the organization of story pieces to form a cohesive storyline. The intra-story piece interface allows for detailed design of text, images, and data labels within story pieces, as well as immersive selection of viewpoints for storytelling. We also include three types of visualizations: 3D heat maps, 3D histograms, and 3D scatter plots. Story authors can choose data visualization types based on data characteristics and narrative needs. As described, we are also supports various tool-based interactions for editing and organizing story pieces, as well as immersive design with each story piece. And here we have a demo. We'll demonstrate the interaction and the output of our system. The Plus tool allows authors to change the time and the attributes of story pieces and create new pieces by selecting existing ones. The eraser tool enables deletion of connections or entire story pieces. Authors can also establish connections between story pieces with the pen tool, and the notebook tool supports dragging and dropping the pre-prepared content into story pieces, while the pencil tool allows for adding and adjusting data labels. The camera tool records viewpoints, capturing spatial temporal data and any added content. And throughout the creation process, our system records spatial temporal scenes and observation viewpoints by story
2 minutes.
pieces. The presentation involves continuous transitions between recorded viewpoints, enabling the audience to navigate through the scenes using controller buttons to switch viewpoints seamlessly. And then we conducted a comparative user study to evaluate our system. We compare it to its non-immersive counterpart, providing identical features in the desktop version, including the same visualization and mouse keyboard interactions. By keeping the story authoring structure consistent and using the authoring environment as a variable, the controlled variable study aimed to investigate the relative pros and cons of immersive versus non-immersive authoring experiences. From our study, we derived 4 key findings. First, we found no significant differences in authoring efficiency between VR and the desktop environments. However, less time was spent moving story pieces in VR. And second, story pieces authored in VR exhibited greater complexity with more story pieces and increased viewpoints, rotations, and movements. Also, users reported greater enjoyment, emotional resonance, and immersion in the VR authoring environment. And finally, when the authoring environment was the same, the rating of VR stories were higher than that of desktop stories. For more details, please refer to our paper. Thank you.
Thank you very much. Thank you, everybody, for your patience. Any questions from the audience? So I have one question. It's a little bit surprising when you showed that the users spend less time moving story pieces in the VR environment. Is there any hypothesis why that's the case?
Yes, we refer to some previous studies, and we find combined with the feedback from the participants, we find it might be in the VR authoring environments you have expensive operating space, which means you can place a story piece at the left, your right, and even your back of your. So when you are authoring story pieces on the desktop, it may overlap with each other. So you may need to frequently adjust the size and the position of each story piece. But in the VR environments, the expensive operating space will make it easier. It's the main reason. Thank you.
All right, thank you very much. So let's thank the speaker. So our next presentation is also remote. It's going to be by Siyuan Yao from University of Notre Dame Volumetric Scenes. Please go ahead.
So
Please unmute yourself.
Okay, can you hear me?
Yes, please go ahead.
Okay, so today I'm gonna present VisNerve efficient multidimensional neural radiance field representation for visualization synthesis of dynamic volumetric scene. So our motivation begins with the challenges involved in large-scale simulations. So these simulations incur significant computational cost and generate the vast amount of volumetric data that leads to high storage demands. And additionally, the size of data also introduce I/O bottlenecks during both saving and loading processes, which makes visualization less efficient. So we have seen existing works that handling those challenges by visualization generation. But for these methods, for example, DN Wolf's InSituNet, GAN VR, they all require more than 10,000 images, and video surrogates would also require the original volume data. So their high data requirements makes them these methods less practical, and also they need long training time, which range from more than 10 hours to more than 1 day. And due to the lack of 3D awareness, the images produced by these methods tend to be low fidelity and low resolution, and also limited the camera views because they're only doing interpolation between training views. So our methods also inspired by based on NERF, and NERF is basically just representing 3D things using neural networks that learning to model the scene from multi-view images and model the scene's appearance and geometry. And so this type of model can render photorealistic images from any viewpoint from the scene. So our VisNerf also adopt factorization technique that's inspired by TensorF and only require 42 images for each scene frames. And we also work with higher resolution and actually like arbitrary resolution because we are using volume rendering. So, and we achieving faster training speed, which only taking like 1 to 3 hours with superior generation quality. And also we support parameter space exploration over time steps, ISO values, transfer functions, and multiple simulation parameters. And our main structure uses a hybrid design, which combines implicit MLPs and explicit feature grids. So in this design speed up the training and the inference, and also improve the generation quality because we have like better expressiveness from the combined structure. And we factorize the spatial feature into matrices and vectors so that we can reduce the capacity from ON cubed to ON squared. And in that way, we are reducing the model size and the GPU memory cost. And we also factorize the feature grid into vectors so that we're reducing the complexity for the parameter space from OM to the power of K to OM. And in that way, we're able to represent a scalable multi-dimensional parameter space with minimal model size overhead. So for the loss functions, we use the reconstruction loss, which is simply MSE between predict and ground truth colors, and also L1 norm loss to reduce overfitting, and total variation loss to encourage smoothness. So with the regularization, we're able to see that the produced images are like more smooth compared to the one without regularization. So this is evident also in the feature matrices, which with no regularization, we will see much more noise. And for the results, the first one is interpolated between time steps using the 5-jet dataset. And for VisNerf here, we're having the highest PSNR SSIM and the lowest LPIPS, which suggesting the best generation quality, and also rather compact model size and the fastest training speed. But it suffers from the slowest rendering speed due to the use of like volume rendering instead of just generating the image directly from the model. So from this example, we are able to see that VisNerve generating the result that closest to the ground truth and are very consistent in different views at, in this animation. So similar results we can also conclude when we are using this for interpolating between different ISO values using the Tangar dataset. And for the qualitative comparison here, we're also seeing the least errors in all views among this method. And we are also doing experiment on like interpolating between different transfer functions. It's actually just like changing the transfer functions. For the first one, we are changing the opacity of two transfer functions. And the second one is more like we're moving the spikes of the transfer functions. So the images would also appear as the changing the both the visible area, also the color. So as you can see, the first one, we can see the opacity of two regions are unchanging. And for VisNerve, we observe very low error in this case. And also in another example here, you can see the change of color and also visible regions. And the last example is interpolating between simulation parameters using the next dataset. We compare it both in direct volume rendering images and ISO surface rendering images. And for the first result is direct rendering images. We're able to see that VisNerve also producing a very high quality result, even we are handling like three changing simulation parameters. And the same for ISO surface rendering. So in summary, VisNerve achieves very impressive speed up compared to both NERV and TensorRF. And beyond this, we also enable scalable and efficient dynamic scene representation, which NERV and TensorRF cannot do. And we also control the model size to be like very manageable, even like we have more like changing parameters. But we still seeing like apparent limitations in this work. So first, when we select sampling views, we not consider optimal view selection, which potentially would improve the training generation quality. We also didn't use flexible number for of views for different scene frames, so which potentially we can reduce the number of training images and boost the model convergence because we're using a smaller training set. And we also didn't optimize for isosurface rendering because for NERV, it's unlike implicit surface representation, which consider more the scene as a surface. So in the future, we might combine this with surface representation methods, which could improve the quality for the isosurface rendering. And the last one is the slow rendering time. So we're considering in the future combining 3D Gaussian splatting with Vis-Nerve framework to enable multi-dimensional dynamic scene generation in real time. So that's it for the presentation. Thank you.
Thank you. So any questions from the audience? Please go ahead, use the mic.
Yeah, a very nice talk. So I was wondering if you considered comparing your work with other nerve-based approaches. So there are several other nerve-based approaches where real-time high-quality rendering is possible. For example, KiloNerve. So have you looked into those and see how your method compares against others?
Yes, we have included such experiment for static scene generation in our appendix, and it's basically for those type of methods. When we are working on this, is just lacking of multi-dimensional works that have been available, like in the field. So we're unable to compare them for the dynamic scene generation, but only compare them for the static scene. Yeah, is that answering what you're asking?
Okay, thanks.
Right. If there's no more question, we'll move to the next speaker. Thank you again.
Thank you.
So our next speaker is also online. Mai-Zhe Yang from University of Notre Dame is going to present meta-INR, efficient encoding of volumetric data via meta-learning implicit neural representation. Please go ahead.
Yes. Hi, everyone. I'm Mai-Zhe, or Michael, a current undergraduate student from the University of Notre Dame, and today I'll be presenting our work on meta-INR, efficient encoding of volumetric data via meta-learning implicit neural representation. So a brief recap on implicit neural representations, or INRs. They have gained a lot of attention recently for representing volumetric data by mapping spatial coordinates directly to voxel values using neural network. It has the great benefits of having high compression efficiency while retaining very high resolution reconstructions. However, a major limitation is that training an INR from scratch for each volume is typically very slow, it's redundant, and offers no reusability across structurally similar data. So this inefficiency becomes a bottleneck for large time varying or ensemble data sets where many volumes share similar structures, but still requires its own separate training for each frame. And there's limited parameter interpretability or reuse. To address this, we propose meta-INR, a meta-learning approach that enables fast adaptation and enhanced interpretability for encoding volumes. So meta-INR is a two-stage pipeline. We have meta pre-training, where we conduct pre-training on sparse subsample volumes to learn a shared initialization. And then next we have volume-specific fine-tuning, which adapts this initialization to full volume data in just a few gradient steps. The key idea is to simulate fast adaptation during training using meta-learning, so the model learns to adapt quickly during the later fine-tuning stage. So during meta pre-training, we use downsampled data, both spatially and temporally, totaling to less than 1% of the original data to obtain a shared initialization between structurally similar data. To do this, we apply a MAML-like algorithm, or model-agnostic meta-learning, with inner and outer optimization loops to train the meta model. The results is a set of parameters that can quickly adapt to any volume in the dataset, offering a strong starting point for reconstruction. So from this prior, once pre-training is done, we switch to volume-specific fine-tuning, where we start from the learned initialization and update the parameters using the full coordinate voxel values for a target volume. So because the model already has a good prior, it converges quickly with just a few gradient steps, saving time while still achieving high fidelity reconstructions. So to test meta-INR, we ran it on 6 different data sets ranging from small to large, and we included both time varying and ensemble data sets. Our baselines are Siren, which is the original INR network trained from scratch, and also pre-trained Siren, which is similar to our meta-INR model, but instead we trained it on the subsample data without the meta-learning. It ended up not being a very good model, as in it failed to capture a good initialization that can provide fast adaptation. So quantitatively, meta-INR consistently outperformed both baselines across all of the data sets. For example, achieves higher PSNR values, it has better LPIPS values as well as chamfer distance. And overall, more importantly, I guess, meta-INR performs much better in terms of encoding time, where it trains on average 5.87 times faster than Siren. So qualitatively, in volume renderings, we see that meta-INR performs very well, often even better than Siren, which trains each volume from scratch. Here we see pre-trained Siren was unable to obtain a very good results because it lacked the fast adaptation that is required for a good prior. And the same story can be said on isosurface renderings, where we see on this relatively tough data set, meta-INR performs the best out of all 3. So moving on to another more exciting outcome of meta-INR is that it has improved parameter interpretability. We used the earthquake dataset and projected the model parameters into 2D space using t-SNE, and the result revealed smooth transitions over time. So here is our results from meta-INR compared to, for example, Siren, whose values are non-interpretable because you train each one from scratch and there are a lot of noise during training. For meta-INR, you start from a common prior, which gives each fine-tuning stage meanings as to which direction the model decided to go with. So here we see that the model forms smooth curves, and for each time step, they form continuous loops. So another experiment we did is simulation parameter analysis, where we use t-SNE on the NICS dataset, where simulation parameters vary. So for example, meta-INR's adaptive parameter clusters meaningfully demonstrated the differences in different parameters, such as H0, which at a lower value is at the more left region of this curve, whereas if you increase the value, it will be at the middle region. And similar story can be said about the inner and outer loops for this other parameter as well. So here is another demonstration where we see that when we fix a volume here at the top, as we move further and further away in this curve, the model gets increasingly distinct, which means that our meta models have is interpretable where it projects into t-SNE.
2 minutes.
So for future work, we aim to incorporate continual learning, which to support incremental adaptation during training, and also grid-based INR structures, which can improve scalability and spatial efficiency. And also, we want to incorporate transfer learning, which can enable cross-stack generalization across variables in multivariate datasets. In summary, meta-INR is a meta-learning framework for INR that dramatically speeds up encoding, maintains high reconstruction fidelity, and enhances interpretability. It generalizes well across datasets and supports advanced tasks like time step selection or simulation parameter analysis. Thank you so much. And any questions?
Thank you. So any questions from audience? Yeah, please go ahead.
Hi, very nice work. So I had one quick question. So you mentioned in your talk that sometimes you found that your meta INR performs better than training a independent model from scratch without doing the meta learning. So can you give some insight about Why is that?
Yeah, so by training each model from scratch, you only have a limited time for each individual time step, as opposed to for meta-INR, we spend a significant amount of time doing the pre-training on large numbers of volumes inside the dataset, where it can learn generalizable structures or similar patterns that can then be adapted quickly during the fine-tuning stage, where we see that it performs better than training from scratch. Yeah.
Okay, thanks.
Okay, all right, we'll move to the next speaker. Let's give the speaker one more. Thank you very much. All right, so the final presentation today in this session is by Junpeng Wang from Visa Research, and he's going to talk about visual attention exploration in vision-based Mamba models. Please go ahead.
Can you project the screen? Okay, get to start. Thank you for the introduction. My name is Junpeng Wang. I'm a research scientist from Visa Research. On behalf of all my co-authors, I'd like to present to you visual attention exploration in vision-based Mamba models. So I'd like to get started with some background about Mamba. When we talk about the sequence modeling, there are two popular machine learning models. One is called RNN, recurrent neural networks. The other is transformer. For RNN, the training is slow because RNN processes tokens sequentially, and there are dependency between those tokens. But the inference time for RNN is fast. But RNN also suffers from this significant forgetting issue. For transformer, the training is fast because the training is just a matrix multiplication, which can be massively parallelized on GPU. But the inference time is slow due to this quadratic computational complexity. The performance of transformer currently is still the best. So Mamba was introduced in 2023, and it's actually good across all three columns. And it's also considered as a potential replacement for transformer, especially when the sequence lengths get very long. So within this short talk, I won't be able to explain what is Mamba in detail. But to understand my talk, you just need to remember two things. First, similar to RNN, Mamba still processes tokens sequentially or recurrently. That means there are token dependencies. Second, each input token has two learnable weights, and that can mimic the attention mechanism similar to transformers. With this, let's directly jump into vision Mamba, which is short for V-Mamba. So similar to vision transformer, we also divide the image into a lot of smaller patches, and those patches will be chained into a 1D sequence and feeding into the Mamba model. So in vision transformer, we will learn an N by N attention matrix, which is telling the attention strings between all possible pairs of image patches. But in vision Mamba, we learn this in a different way. We just learn two vectors, C and B here, which are in the shape of N by 1. You can imagine this is much easier to learn than learn this N by N matrix directly. And then after we learn those two vectors, we just do C multiply B transpose. We also get a N by N matrix, which has the same functionality with the original attention matrix in the transformer. As I told you earlier, right, this vision Mamba process tokens sequentially. That means for each patch, it can only see the patches before the current one. Like for the red one, it can only see the patches scanned through by this blue scan line. In order to make this patch see all the rest patches, we can scan the patches in the reverse order. So when we reach this red patch, we just average the two attentions from the two directions. In fact, for Vision Mamba, it's actually using four-way scan to take care of both horizontal and also vertical locality. So this animation will show you the four routes of those four scans. And at each patch, we just average the attention from the four directions, and then we get the attention. So the first contribution for this paper is we introduced 3 new patch scanning orders. The first one is called the diagonal order. You can see we just scan the patches along the diagonal line. So this will make sure the patches along the diagonal line can maximum maintain the spatial locality. Second one is called this Morton curve, or the Z curve order, which is well known for maintaining the spatial locality. And the third one is called the spiral order, which just scan the patches following this spiral circle. You can imagine the innermost patch will have the best spatial locality. So what I have told you so far is only happened within a single Mamba block. But for Mamba model, we will have multiple Mamba stages. And within each stage, we will have multiple Mamba blocks. So the concept of stage and block is similar to the concept of layer and height in Transformer. And we have 2 research questions. The first one is, are the attention patterns consistent across different Mamba blocks, which we call the inter-block attention pattern? The other is, within a single block, how is the attention spatially distributed across the patches, which is intra-block attention pattern? To save time, I will directly tell you for the first question, we found that the attention pattern in different blocks are very different. And then let's focus on the second question. What is the attention pattern within a single Mamba block? So let's assume we divide this image into 16 patches, 4 by 4. That means we will learn an attention matrix, which is set by 16 by 16, right? And using dimensionality reduction algorithms, I can reduce this to 16 by 2. 16 are the 16 patches, and 2 is the 2 coordinates. And using this, we can visualize it as a scatter plot. And we can use a point size and color to denote the row and column of the corresponding patch. So if you can see on the lower left, this image are the patches from the stage 1 block 0. Obviously, we can see a lot of small clusters. And if we highlight those clusters, you can see those are the patches from the same row or the same column. So basically, this is telling us patches from the same row or same column will share the similar attention pattern. And when we click individual patch, you can see patches in this block will always attend to patches before the current one. I can change to different patches. You will see the pattern still remain, right? It's always attend to the patch before the current one. And the word before is defined according to the cross-scan order I mentioned earlier. Basically, this is the cross-scan order. Okay, so if we change to other blocks, the attention pattern will be different. But let's just focus on this. Just focus on this block, and let's see the 3 new orders we introduced. So here's the scatter plot, and you can see that spatially closer patches will fall into the same cluster. Let's focus on the first one. This is the diagonal order, right? If you look at this cluster here, those are the patches along the diagonal line. Since they are spatial closer, they also show similar attention pattern. And this is also true for the Morton order or the spatial order. So now if I click individual patch, you can see on the very right, so all the patches in this block, stage 1, block 0, will always attend to the patches before the current one. But the word before, again, is defined according to our patch scanning order. If this scanning order is diagonal line, then all the before means the patches before the current one following the diagonal order. But if this order is this Morton order, then the before will mean those ones. That means before, because we have this patch order defined earlier. Okay, in short, we conclude the 3 things in this short paper. The first one is the attention pattern across different Mamba blocks are very different. But due to time limitation, I didn't explain this in detail. You can check our paper for details. Second one is the spatially closer patches often show similar attention patterns. And lastly, the order of image patches significantly impact the attention pattern in Mamba models. Thank you for your listening, and I'm ready to take any questions. Thank you.
So I have a question. So the ordering
and then those sort of patterns that you choose.
Yeah.
Is there a connection between this and the interpretability of the model itself?
Yeah, actually, we introduced those new orders originally because we think the very initial order, which we call cross-scan, does not maintain the spatial locality very well. If you see the first row, anyway, if you go here and directly jump to here, there's a spatial jump. So this will not maintain the spatial locality. And then we actually try some order, like we do this way and then back forth, just to maintain the spatial locality. We originally believe this will better maintain the spatial locality and increase the performance of Mamba. But it turns out we didn't increase the performance, but we show, some way of perturbing the attention patterns using different orders. So in the paper, we conclude something, but we didn't draw a strong conclusion regarding the performance. But from the interpretation-wise, we believe this will help us better understand the attention between those patches. Thank you.
So that's conclude our session. We're only 3 minutes over time. So take care, everybody. All right, now it's break time. Get some cake.